The hourglass. This timekeeping device has been around since about 150 BCE and is remarkably still in use. Today it exists primarily as a convenient way to time the boiling of an egg, but historically it provided a relatively reliable measure of time, even in a maritime setting. It outclassed its main competitor, the water clock, due to its approximate invariance to external conditions. Obviously, it didn't suffer from problems involving condensation, but its reliability also came from the nature of the sand inside it, which exhibits unique characteristics because it is a granular material. Granular material is a conglomeration of small solid objects that exhibit liquid-like flow behavior when viewed collectively. How can we analyze this behavior? One way to look at fluctuations in a signal is through Fourier analysis. Joseph Fourier was a French mathematician and physicist who worked in the 19th century. He invented a way to take a time-dependent signal and show the frequency-based structure of the signal. We can see the various dominant frequencies present in the previous time domain signal in this graph. If we take this clip of famed operatic tenor Luciano Pavarotti, we can look at the frequency spectrum of this emotive tenor C5. Looking at the labels in this graph, one might be surprised to see that C5 is not the dominant frequency of this clip. This is probably due to the other instruments as well as the vibrato in the note. We can also decompose a signal that is much less well-defined, like Niagara Falls. As you can see from this spectrum, there is not one dominant frequency in the signal, but the strongest frequencies are between 10 and 100 Hz, on the lower end of the human hearing range. Alright, we've talked about how to analyze an oscillatory signal, but what is the data we're talking about? We are first going to be looking at an optical signal. This is often generated by a laser, but in our case is an LED light. Though this isn't an audio signal like we have previously analyzed, our optical signal also provides a time domain dataset that can be decomposed using Fourier analysis. Our setup is an LED signal captured by a photodiode, focused down with a microscope element. We place an hourglass as shown between the light and the detector, and detect sand flow as a drop-in signal. We can take this signal and play it back as a sound. I have included a graph of the time series as well. We can see in this graph that there are some strong low-frequency effects present in the signal we listened to a moment ago. There remains interesting analysis to be done in this system that is a bit out of the scope of this video. This experiment is in its infancy, and we know very little about this system and what to expect from the data. Currently, we do not know the broader impacts of this study, but we hope that it will lead to new questions, and in the short term, it provides a pleasant challenge and an opportunity to use Fourier analysis in a real setting.